Hi, this is Josh Quinlog, and this is the analysis demonstration for Statistics for Institutional Research. So first we're going to start with the research question. I've decided that the president of the university has approached the IR office and expressed an interest in identifying academically at-risk students. The question at hand is, can we use data about our incoming students to identify those that are likely to be academically at risk so that we can provide educational resources or assistance upon matriculation? So the data, based on her prior research in higher ed, the president has asked that we look specifically at parents' education level, high school rank, students' age, and standardized test scores as possible predictors of students' academic success. We're going to use the fake NESI data set, which includes the following measures. Our dependent variable will be the cumulative undergraduate GPA at the end of the semester in which they took the survey. The independent variables will be the age group, mother's and father's educational level, high school rank, SAT scores, and SAT scores. Because we have one scale dependent variable and multiple scale independent variables, we'll be using multiple linear regression to analyze the data. So on to the analysis. Here's our fake NESI data set, and the first thing we're going to want to do is run some descriptive statistics. So we're going to come over here and run descriptives. I've already entered all the variables in that we want, options, okay, kurtosis and skewness. I think we look good. So we're going to go ahead and paste that. And let me bring that screen up here. We'll go ahead and run it. And what we get here then, the important thing to look at here is our N. We had 857 records, but we only have 125 valid records list-wise, and that's because we're missing quite a bit of data. We're missing a lot of ACT scores, some SAT scores, and high school rank are the most common ones. So at this point, what I want to do is impute those missing data points because that's far too many missing. And I went and learned all about multiple imputation and then went up here and realized that my version of SPSS does not include that and I couldn't get it added. So instead, I noticed that ACT and SAT scores are essentially measuring the same thing. And so what I went ahead and did was found the concordance tables for SAT scores, and I created a new variable. And the new variable is the ACT score when available, and then the estimated ACT score based on the concordance tables from the SAT scores for the remainder. So we'll take a look here at the new variable that I've created at the bottom. We've called it entrance exam, and it's the ACT score when available, otherwise the concordance value based on the SAT. So now let's take a look at that. And descriptives, we're going to run frequencies this time because I want to look at a histogram. Again, I've entered in the same variables that we were looking at, but this new one that I've created is there. Statistics, we've got what we need there, and for charts, we learned on histogram, and so we'll paste that in and go ahead and run it. And here what we see now, the missing values are up here. We're still missing quite a few in high school rank. We're just going to have to deal with that with our data set. But now in our test scores, we have 601 records, only 256 are missing. So we're doing a lot better. We're still missing quite a few people in this data set when we look at this list-wise, but I think we're doing okay for the analysis. We're going to skip through the frequency tables here and come down to the histograms. We want to make sure things are fairly normally distributed, although that's not super critical. But here's the dependent variable. This is our GPA, and it is a little bit negatively skewed, and we'd expect that because most people have GPAs between 2 and 4, very few below that. If you're too long with a score like that, you're probably going to be kicked out of school. So that makes sense to us. High school rank, the better you are, the closer you are to 0, because this is a percentile rank, and so 0.01 would be top of the class, and 0.99 would be in the 99th percentile of the class. When we look at education level of the father and the mother, we're going to see a slight bimodal distribution, and that kind of makes sense because this category will represent high school diploma and this college diploma, and those with some college probably are fewer. Same over here with the mother's education. And then age, we use the age category variable, and we can see that those younger ages are going to be far more common in the undergraduate population. Finally, our newly created variable does have a fairly nice, fairly normal distribution here of the ACT scores and SAT score concordances. So, with that all done, we're going to go ahead and run our regression analysis. So we're going to choose linear regression and go ahead and run that. Now, I've pre-populated this with one variable in each block, so we'll go back through these blocks. We've got our age category here, high school rank, got the ACT score, that's our new variable. We've got father and mother's education level. So we'll go up here to statistics. We want to see the R-square change. We'd like to see some descriptives and the collinearity diagnostics. We don't need any plots. I don't think we'll need anything there either. So we'll go ahead and paste this. And run it. Okay, so up here we've got our descriptive statistics and then our correlations, and I want to take a look at the correlations. We can see that the independent variables all have statistically significant correlations, with the independent variables that we're looking at. We can also see there's some strong correlations. For instance, 0.395, fairly strong between the mother's education and father's education levels, and we kind of expect that. But that number might mean that we'll see some collinearity issues because it's possible that these two variables are essentially measuring the same thing. Scroll down here and take a look at the model summary. And we can see as we go through, we're building a more and more predictive model here. We end with an R value of 0.486, which explains about 23.7% of the variance. That's our square value. And if we look over here, the F change is significant all the way to the very end. So this fifth model actually doesn't change at all really from the fourth model. And so we'll take a look at that when we get to the bottom. The ANOVA, we can look at that. We have the F statistic here, all of which are statistically significant, although that F value drops a little bit in this last model because the regression model isn't any stronger. The degrees of freedom for our residuals are a little bit lower, lowering that, or raising rather, that mean square value. So here we look at the coefficients for each of our blocks, and we'll scroll down. We're doing pretty good. We see some really significant things till this very last block. We add in the last variable of the mother's education, and that's not statistically significant, and that's kind of what we saw up above. It's really not helping the model at all. We can look at the collinearity statistics and see that we're doing all right there, so there isn't really a multicollinearity problem with the mother and father's education, but this really isn't adding much to the model. So I think what we're going to do here is go up and go back into the linear regression. We're going to go ahead and remove this last variable as it's not really adding anything to what we're looking at. Click OK. And now we're going to see the same correlations, but in our model summary here, we build up to that R value of 0.486 in our fourth model, and that's identical to what we had in the last iteration. So we're going to come down here and take a look at the coefficients. Again, the VIF score is below 4, no real problems with collinearity. We see statistical significance with all the t-values here. We can look at the standardized betas and see essentially which values, which variables are providing the most significant relative impact on the regression model. And then we're going to look over here at the unstandardized coefficients, the unstandardized beta, because between the constant and these variables, we can now use this to build a model to have a point prediction of what we predict their GPA will be, and that could be useful to answer that question that the president has posed. We may also want to look at a 95% confidence interval. So we're going to come back up here to the regression and run this one more time, and we're going to add the confidence intervals, a 95% confidence interval. We'll paste that. Come back in here and run it. And we're going to scroll right to the bottom where we see our coefficients. And now we see this 95% confidence interval for our beta. And so we can use these values as well to produce a 95% confidence range for any given student if we have these variables known to predict what their GPA range is likely to be. This can obviously be used to create some models to look at students and answer the president's question and provide those resources for students who may be on the low side of things early on. And we'll talk about that in demonstration support in the next assignment. So I think that gets us through the demonstration analysis. If you have any questions, let me know.